These are notes for lesson 47. So let's get started. We're going to talk about applications and models of exponential growth. So let's look at an example here. It says, how long does it take for my investment to double if I was given an annual interest rate of 4.2% and interest is compounded continuously? So first of all, notice that interest is compounded continuously, so that means we're going to be using PERT. So it says, how long will it take for my investment to double? Notice it doesn't actually give us the amount that we're investing, so we could actually choose anything. The easiest number to choose would be 1. So let's let P equal 1, that's our initial investment, and that means A, since we want it to double, would be 2. And of course R, if we write it as a decimal, will be 0.042. Let's go ahead and plug the numbers in. Now, let's see, we don't really need this 1 here. So we have an exponential equation. Notice we have the base, exponent, answer. And so let's write this in natural log form since this is base e. I'm just going to write it as log base e of 2 equals 0.042t. And of course, this would be a natural log. So let's go ahead and solve for t by dividing each side by 0.042. And so t is equal to the natural log of 2 divided by 0.042, which is approximately 16.5. So our answer here is about 16.5 years, or 16 and a half years. Let's move on to the next problem, but before we do that, we need to talk about a new formula, although it's really not new. So often quantities that experience exponential growth or decay can be modeled by the formula y equals y naught times e to the kt power, where t is equal to time. Now y naught represents the initial quantity at time t equals 0. K is the rate of growth or decay. If k is greater than 0, then we have growth. If k is less than 0, then we have decay. Now this formula is actually very similar to something we've already have seen. Think of PERT. In fact, P, hold on a second. P is the initial amount invested. Here it's just the initial quantity. Y naught represents the initial quantity. R is usually our interest rate, which for this problem it could be growth or decay, a rate of growth or decay. And T is still for time in years. And so it's very similar to what we've been doing when we work with this formula. It's very similar to what we've done with PERT. So let's look at an example. So example 2, the population of a small town can be estimated by the function P of t equals 2,658 times e to the 0.04t, where t is the number of years since 1990. So we're going to answer two questions here. First is, what was the population of the town in 1990? And the second is approximately what was the population of the town in 2005. So if we look at this formula, y is p of t, y naught is 2,658, and notice our k here is going to be 0.04. So the population of the town in 1990 was the initial population at time 0, which is y naught, or 2,658. Approximately what was the population of the town in 2005? Well, since 1990, that's been 15 years. In fact, we could subtract 2005 minus 1990, and so t is 15. So really all we're finding here is p of 15. So we'll plug in the numbers, and you should get about 4,843.19, but we're talking about people, so it's about 4,843 people. Let's move on to our last example. So the city of Pearland has experienced exponential growth. In the year 2000, the population of Pearland was 37,640. In 2008, the population was approximately 90,700. So again, we're going to answer two questions here. The first is going to be, what was the exponential growth rate of Pearland? And the second is, what is the double time? In other words, how long does it take for the population to double? So let's go ahead and take care of A first. So we have our formula, y equals y naught times e to the kt power. If you plug in the numbers, the initial population was 37,640, so that's our y naught. And it grows to 90,700, that's going to be our y. And that was in a period of 8 years, since it's the population since 2000. So this is the equation we need to solve for k so that we know the growth rate. So we'll divide each side by 37,640. So now we have the three parts. Our base is e, the exponent is 8k, and the right side here is my answer. So we have base, exponent, answer. Let's go ahead and write this in exponential form. And I don't want to lose any accuracy here, so I'm just going to leave that fraction as it is. We also need to divide by 8. So let's go ahead and find k. If you plug this into your calculator, you get about 0.1099. As a percent, it's about 10.99%, and which we normally give rates of growth or decay as percents. And I think 11% is probably a good enough answer. If you said 10.99, that would be fine. But I'm going to round to 11% here. So now we know what k is, and so we can write a formula. We have y equals y naught times e to the kt power, and we know y naught, our initial population in 2000, and we know k, so let's go ahead and plug those in. And notice also, actually I'm sorry, in this case, let me go ahead and stop this for just a Alright, so I had to fix a mistake. So we have y equals y naught times e to the kt power. Let's go ahead and plug in y naught, which is 37,640, and y needs to be double that, which is 75,280. So the main thing is finding the number that's twice 37,640. So now when we divide each side by 37,640, we get 2 is equal to e to the 0.11 t power. So we have an equation in exponential form. Let's go ahead and put it in logarithmic form. And we still need to get rid of that 0.11. So we divide each side by 0.11. So t is going to equal natural log of 2 divided by 0.11, which is about 6.3. So our final answer here is 6.3 years. Now if you wanted to, you could go back and plug in 6.3 for t, and you could verify that you do get 75,280 if you plug in 6.3 for t. That's it for this lesson. Good luck on the homework, and we'll see you for the review tomorrow.